Hello, everyone. My name is Evan Dewald. I'm a graduate student at Carnegie Mellon University, and today I'll be presenting my research on Additive OS, which is an open source platform for additive manufacturing data management and intellectual property protection. I'm going to start with some upfront conclusions. First and foremost, Additive OS is a truly open source platform for helping you manage your AM data and secure your IP. We're using smart contracts to address significant vulnerabilities that exist in this AM digital thread to actually store our content and maintain meaningful relationships between our AM data, for instance, builds, parts, and output properties using a directed acyclic graph representation of this hierarchy. To store files and share them around, we're using a peer-to-peer file storage and content delivery network called IPFS. In addition to allowing us to host our own data, this has the opportunity to minimize latency in our content delivery and increase the precision through which we share files through a content-based addressing scheme. And finally, as an open source solution, while Additive OS is currently packaged in a browser-based application, the underlying APIs allow for complete customization, even on low resource hardware. So you can run this client on something like a Raspberry Pi that's collecting in situ monitoring data, or extend it to suit your needs as a data scientist. I want to start with some quick background. We'll be using a blockchain concepts to secure our digital thread in this application. So what is a blockchain? On a highest level, a blockchain is an immutable append-only ledger that's distributed among a network of individual nodes, which are just computers running the software client. And because of the way these blockchains, while they vary in what's called the consensus protocol, essentially what they all have in common is extreme fault tolerance. Attackers would need to control a massive amount of computing power if they wanted to even attempt to alter the ledger. The way we interact with blockchain in this application is through the use of smart contracts, which are just computer programs that execute the business logic that allow us to interact with the blockchain by using these predefined functions that we set up. So an example of a smart contract would be the terms through which you transfer funds from one account to another. First, you need to make sure that the withdrawing account has sufficient balance. And then after the transaction, you want to make sure that both balances are reflected accurately through that transaction. And the key takeaway here is that using a public blockchain like the Ethereum ledger allows for an independently verifiable audit trace. So while there are a lot of ways to keep an audit trace, you could something as simple as an Excel spreadsheet or an internal database for your company. These are not truly independently verifiable by external parties, whether those are regulators or end users. And the AM supply chain, to its benefit and to its advantage, is meant to be pretty distributed. Sometimes there are different organizations that handle the designing, fabrication, post-processing, and those may all be different from end users and regulators. So we want all these parties to be able to independently verify this immutable audit trace through a public network. And then bringing us back to additive manufacturing specifically, I want to talk about two of the main security threats that we see in additive in the literature describing these attack vectors. So the first would be a man-in-the-middle attack or sabotage. The simplest example that you'll hear about, and the most common one people think of, is to imagine that in between when a part is designed and when it's fabricated, some malicious actor intercepts this file and embeds a tiny defect, and that could lead to catastrophic failure. But really, these sorts of vulnerabilities exist not just in our design files, but all throughout this digital thread. So for instance, process monitoring data is increasingly being used as a means of certifying and qualifying parts. You can imagine a pretty sophisticated attack where in reality, the build resulted in some heat buildup that would usually raise concerns to a regulator or a user. But the attacker changes the pyrometry data to indicate that there were nominal conditions throughout and no cause for concern. The second bucket of attacks that you'll see is counterfeiting and IP theft. And so the traditional way through which we establish ownership of a design or some sort of intellectual property is through patenting or copywriting. If you've ever gone through this scenario yourself, you know that this is expensive and time consuming. And again, specific to AM is that often we're dealing with pre-production proprietary designs that are really just rapid prototypes. It doesn't always make sense to go through this public disclosure of these early stage concepts. So I want to go through 2 case studies, and then attached to this presentation are videos showing demos of how this is addressed using Additive OS. We'll just go through a schematic overview of 2 of these attack vectors. So this first scenario is based on that sabotage attack. And again, the concept is after this thorough design review, we finally approve this rotor blade design. But in transit between our designer and to the actual fabrication step, some malicious actor embeds a tiny micro defect in our CAD file that, if printed, would lead to catastrophic failure. So the question is, as the printer, how do you verify that the part you have is authentic? You could simply compare the file names. In a lot of cases, this is good enough. It sounds silly in this scenario because obviously it won't work. It's easy enough to save a file under the same exact file name. You could manually inspect our files. This, due to the highly iterative nature of AM, is simply not feasible at each of these design steps. Each time the file changes hands, to manually inspect it is not the best option. And you could compare the hashes, the cryptographic hash between the 2 files. This is a common way to assess data integrity in a lot of software domains. But the question is, where do you store that hash of that verified file? Do you store it in an Excel spreadsheet or in a centralized database? We're assuming in this situation that if the attack vector or if the attacker has access to change our files in transit, these other sources where it's a centralized database may not always be, they could also be vulnerable as well. And moreover, if you're a regulator or an end user, you're simply trusting that that file that's in that database is accurate, and you can't really verify for yourself. So again, here's a schematic of this attack. Again, our saboteur is intercepting the file. And how do we verify authenticity of the part? Where do we store that file hash essentially, so that our printer can independently verify for themselves that they have the proper file, approved file? What we're going to do in Additive OS is introduce a smart contract where this is going to store this is essentially a data structure that's going to store some metadata about who signed off on this project and an index. It's also going to store the hashes of any files associated with this project that we want to be independently verifiable. So in this CAD file scenario, we'll store the hash of our approved file in this smart contract. Any regulator or end user can go back and see that transaction, when it took place, who signed off on it. And then for the purposes of our printer, all they have to do is compare the hash of the file they've received to what's stored in this smart contract. They'll see that there's no match there and the file has been tampered. These hashing algorithms have a property called the avalanche effect, where even if a single byte is changed in that input file, it'll result in a drastically different checksum. And this is why they're so advantageous for data integrity purposes. So what are the benefits here? This was a trustless interaction. Whether you're inside this scenario or outside it, you can independently verify exactly what was happening, but you're not exposing the sensitive data to this public ledger. All that can be seen by anyone else is just the file hash, which is kind of meaningless to anyone else who might be interested in watching this transaction. And while we saw an example here for a CAD file, the entire supply chain can be secured in this way. We can add file hashes for any file, whether it's 5 gigabyte process monitoring data, test data, billing reports. We can secure in exactly the same way. and maintain that integrity throughout our digital thread. So again, there are demos attached. I encourage you to check out the attached video to see how this works in Additive OS specifically, how you could verify and sign transactions without managing the private keys within the application itself. And then as the printer, you can go back and verify that the file is authentic. The second scenario, as we said, is related to licensing and IP theft. So the scenario here is a designer sends this proprietary widget design to a service bureau under the terms that they want it to be printed no more than 10 times. The question is, how do you enforce this license, ensure authenticity of any parts as the end user? This is a trusted interaction. We're relying on different parties to keep their own records, both honestly and accurately. And then as the designer, if your design is stolen, how do you prove that you owned that part, that design, without going through a public disclosure? And how do we maintain that that's admissible evidence if it did come to a legal dispute? So what we're going to do, again, is deploy a different smart contract that this time will store information about the two parties involved. These will be the only two privileged entities that can sign off on licensed prints, so the licensor and the licensee. We'll also store the hash of the part to indicate ownership of this IP, because you can always prove that you had ownership of this file that produced this hash at this time. And we'll also log a number of licensed copies that we'll allow through this license. Each licensed part now we can link to an independent, unique digital certificate of authenticity, which to link between this digital domain and this physical domain is simply a QR code that when you scan it, you linked to the information about this transaction, which licenses it's related to, who is involved, and when it happened. And so if you're looking for inauthentic copies, they would either not have this license, or it would be a duplicate of another license that already exists, which is easy to identify. This transaction, as we said, provides evidence that you own the IP without going through purely legal options. But if it came to a dispute, several states now, and it's increasing all the time, now accept smart contract transactions as admissible evidence. And you're doing this in a public domain, so there are no questions about how you stored the files, how you produce that integrity for yourself. Again, a demo in the associated link about how we create a license, log prints, and then assess the authenticity of these licenses, print out a QR code that you can attach with your part, scan it to see those digital license details. Now I want to get into the data management infrastructure. Additive OS, while it has these security benefits, it is also a great way to store your AM data and the relationships within it so that you can unlock meaningful relationships between inputs and outputs. And so when it comes to storing data, AM data specifically, we have this really flexible schema where we have to be able to capture relationships between builds, parts, process inputs and outputs. And we want this to be queryable, flexible, and interpretable to anyone else. So the traditional ways of doing this, SQL database or folder-based storage, they have limitations in terms of their flexibility or their aggregation capabilities. But in Additive OS, how we're storing data is in what's called a directed acyclic graph. So of course, a graph is just nodes connected between what are called edges, and a directed graph shows a direction of these edges. So in our case, parts inherit the properties of the build, and characterization data are coming directly from each of these parts in this case. And so these are queryable and collapsible because we're storing them in a NoSQL database, which is flexible and meant to handle highly scalable data sets. And then for our purposes, we can use content-based addressing to actually highlight the individual nodes and the content that's stored there, as opposed to a name like in these folder-based structures. So again, in Additive OS, we are storing data within these spreadsheets where this ontology, this hierarchy, the relationship between nodes and edges is stored actually through a naming convention. And this is an intuitive way to capture the structure of entire builds, whether and is independent of the machine that you used. And so Additive OS directly imports these spreadsheets and then allows you to attach characterization data, test results, visualize all this data and how it relates to each other. It's also exportable to a format that can be used in something like PyTorch or TensorFlow to capture graph neural network representations, because really the relationships between nodes are just as important as the information that's stored within the nodes themselves. So now when it comes to file storage, what are our options here? As a cloud-based platform, we want this stuff to be accessible by anyone, anywhere, as long as they have the proper permissions, of course. So we could use something like AWS 3, which is sort of the standard when it comes to programmatically accessible file storage. But the problem here is the way AWS structures their platforms to be fault tolerant is you have regional data centers that actually store the data. So if you upload a file and you only have regional access to, for instance, the Northern Virginia data center, if somebody in Japan now wants to access that file, they have to download it all the way from Northern Virginia. Unless you have a really expensive content delivery network, it's difficult to scale this platform and make sure that this data is highly available regardless of geography. And the question is, if I'm saving this file to my local hard drive anyway, why can't I just make it accessible to others? And this is the idea behind the Interplanetary file store, which is a peer-to-peer file storage platform and content delivery network, where essentially each node, which is just a computer running this client software, hosts only the files they're interested in. So for instance, my AM files. And now if somebody else wants to access those files, they can download it from a swarm of peers, anyone, which is just anyone who's saying that they are hosting this file. So now if somebody in Japan wants to download a file that's stored on my machine, they have to download it from me once, and then they can host it out to anyone for local content delivery within that region. And so this is a way to rapidly scale the accessibility of our files. But of course, everything we're storing on IPFS is encrypted so that only people who are privileged to access it can see it. And then you see a performance increase here because when I put upload in quotes, because with IPFS, everything is still just stored locally. So you get really big performance increases, especially when it comes to upload speeds, because you're not delivering this to a monolithic data center somewhere else. And then finally, what I'm really most excited about is the full customization that an open source platform allows for. So you'll see Additive OS as it is in a browser-based application. That's just one way to access these methods. So really quickly, in just a few lines of code, you can run this on this client on low resource hardware like a Raspberry Pi, and for instance, directly send your acoustic data right to the same network without having to go save it to your desktop and really connect all the devices, the internet connected devices within your laboratory in this way, and apply that data integrity benefits along the way. We can also synchronize our pin sets for what's stored on IPFS, so that if my computer is the one hosting the data, I can synchronize it so that other servers that are always on are also hosting my data in case I turn off my computer. and everything, the database can be directly accessed and by any by data scientists using any programming language, really, whether that's MATLAB, C++, Go, Rust, JavaScript. All of these, this is meant to be useful for data scientists as well, so we can unlock these important relationships and really scale our data storage as we go. So just to wrap up here, as I said a couple times, I'm linking a video that has these demos of the different aspects and how they actually work within the platform. And if you're interested in running Additive OS, I'd love to hear from you. I'm working on documentation so that you can set this up in your own facility. And then once it's set up, it's easy to add users and really get going. But I'd love to hear from you, your experiences, and if you are having bugs along the way or building new things with Additive OS. Thank you, and thank you for hearing my presentation.